Okay, so in front of us we have a GTX 1080 Ti. This is the Hall of Fame edition by Galax. So for those of you who are not complete losers like me, this is a liquid nitrogen overclocking card. It's one of the basically the best 1080 Ti you can get outside of maybe the Kingpin, which I've actually had this week as well. Very nice card. Anyways, like other broken cards we get, we want to first start by checking for a short on the base voltage rails. So I have my multimeter in continuity mode. If I probe something connected to the ground, like ground itself, my multimeter beeps. So to start with, we're going to check 12 volts and 3.3 volts. Shit. To check 12 volts, we can get away with checking any one of the first 3 pins on this side, and we're perfectly good. To check 3.3 volts, we can start at this notch and go 4 pins left. Again, perfectly good. Now we want to go ahead and check 12 volts at the 3 external 8 pins. Is that flux or is that just burnt plastic? Oh, that's burnt plastic. So, checking the leftmost 8 pin on this inductor, we're perfectly good. Checking the middle 8 pin on this inductor, perfectly good. And checking the rightmost 8 pin on this inductor, we're perfectly good. Now we want to go to regular resistance mode and check the voltage rails generated by the card itself. So I should note that there are a couple of extra rails that you see on overclocking cards that you typically don't see on regular cards. So for example, this card has multiple 5-volt rails, and it also has an extra 3.3 volt rail. So we're gonna start by checking the 5-volt rail. So the 5-volt rails is first one and the main one, I believe, is this one over here. And we have 10 kilo ohms, perfectly fine. The next 5-volt rail is this over here, so 508 ohms, perfectly fine. And finally, the last 5-volt rail is an LDO on the back. It's this LDO, and we'll be checking this tab. In fact, we'll just check it now. And as you can see, we have 507 ohms, which is very similar to the 508 of the other one. I should note that they're not the same 5-volt rail, despite a very similar resistance. Okay, so now we want to check 1.8 volts, which can be found on an inductor over here. And checking 1.8 volts, we have 227 ohms. I should note that these are liquid nitrogen overclocking cards, because they have rather weird PCBs, they can also have rather weird resistances. For example, on the 1080 Ti Kingpin, 1.8 volts would be around 600 ohms, and a little higher or a little lower depending on where you set the BIOS switch at. However, in this case, I can tell you that 227 ohms is actually still too low for a Hall of Fame 1080 Ti. And I know this because I can compare it to my Hall of Fame 1080 Ti. As you can see here. So, if we check my personal Hall of Fame 1080 Ti, you'll notice that we have a rather familiar 800 or so ohms, which means that we have an abnormally low resistance on the customer's Hall of Fame 1080 Ti, and that by extension we likely have a dead core, given that an abnormally low resistance on 1.8 volts is accompanied by a dead core well over 95% time on Pascal, and I would say Turing as well. But anyways, I'm not willing to give up on the card just yet, despite the fact that the odds are not exactly looking too good. So let's go ahead and measure the resistances of the memory phase as well as the PEX rail. So checking the memory phase itself, memory rail I should say, we have 65, 66 ohms, which is perfectly fine. That's roughly what I get on my personal 1080 Ti Hall of Fame edition. And checking the PEX rail, we should see something that's about 40 plus, but I should note that there's quite a bit of variation on 1080 Ti's. And in this case, we have 65 ohms, which again is perfectly fine. So despite the abnormally low resistance on 1.8 volts, which by the way, generally signifies a dead core, well over 95% of the time, I don't really want to believe it's a dead core, even though I kind of know it probably is. So let's go ahead and at least plug it in and power it on and see how it behaves before we come to any conclusions. Okay, so let's go ahead and power it on. We're going to start by checking all the 5-volt rails. So checking this one, we have 5 volts. Checking the one up top here, 5 volts. Checking the one on the back, 5 volts. Checking 1.8 volts, we have 1.8 volts as expected. Checking the V core, which turns on next. That's 700 millivolts. So we can tell by the fact that it's at 700 millivolts that the GPU itself is actually initialized. It has. So that means that we must have the PEX rail, which is at 1.02 volts, more or less. Yep. And that we should also have the memory. But we don't, actually. So that's why it's taking so long to post, because it behaves as if it has memory problems. Okay. So as you can see, we're missing the memory phase. And as you probably already saw, we have a bit of a solder flux around the PWM controller for our memory phase. So I should note that this is a UP9509P. And I haven't actually looked at the datasheet for this yet, but I'm hoping that maybe somebody just bought to repair and that this card is actually fixable. But of course, we won't know until we at least restore power to the memory rail. So let me go ahead and look at this datasheet, and then we'll go over VCC, enable, refin, and VREF at minimum. Okay, so I should note that the reason why we're still trying to restore the memory phase is because I have a slight inkling of hope that this card is actually repairable despite the abnormally low resistance on 1.8 volts. If you don't know, the thing GDDR5X takes 1.8 volts as its pump voltage, and our abnormally low resistance on 1.8 volts could be actually caused by a memory module, and that's why I'm still trying to repair this despite the fact that the odds are not exactly in my favor. Anyways, so as mentioned, we want to start by checking VCC and enable. So we're going to start by checking enable. Enable can be found on the the bottom end of a resistor over here. VCC can be measured on the left end of this capacitor here. Ref in can be measured on the right end of this resistor over here, and Vref can be measured on this end of this capacitor over here. Okay, starting with our enable, we have 3.1 volts, perfectly fine. Checking VCC, 5 volts, perfectly fine. Checking ref in, 0 volts. Now let's check Vref. So Vref is ref in is derived from Vref, and we do have Vref. Okay, so we have Vref, but we don't have ref in. So ref in is the reference input voltage for the memory phase. So if ref in is, say, 1.5 volts, the output of the memory phase should also be 1.5 volts. If ref in is 1.1 volts, then the output should be 1.1 volts. So anyways, we have a problem with ref in, obviously. We need it to be about 1.35 volts in order for the memory phase to turn on. I'm going to go ahead and look at the components under a microscope and take a few measurements, and in a moment you'll see what I find. Okay, so as mentioned, ref in is supposed to be 1.35 volts, and it's derived from Vref, which is 2 volts. So I actually know why we don't have ref in. There's a resistor over here that is supposed to be about 200 ohms. However, if we measure this resistor in circuits, I should say that the resistor measures as 200 ohms in circuits, so it might not actually be 200 ohms. We can see that we get 116 kilo ohms, which is far too high. So this resistor is likely the source of our problem. I have to confirm what this is actually supposed to be, and in a moment we'll switch it out and see if the card becomes any more functional. But there's actually something I want to test first. So unfortunately I haven't tested what the symptoms of this card are. So let's go ahead and hook up a display and see if this at least posts. I should note that a card like this would likely take about a minute to post. When it does, it'll do so with the monitor backlight on but no image. So let me go ahead and confirm. Let's go ahead and confirm the symptoms first, so I have a subtitle for my video. And as you can see, we have a backlight over here, and the LED indicator has gone on, and the backlight on the monitor has turned on, but there's no image. Okay, so that confirms the symptom for our card, and by extension gives me a subtitle for the video. Anyways, let's go ahead and replace the resistor over here and see if the card becomes any more functional. Okay, so as you saw, I replaced the one of the reference in resistors over here. It is actually 200 ohms, by the way. And actually, so before we power on the card, let's just confirm or double check that the resistance of 1.8 volts is actually 227. Yep. So with all that done, let's go ahead and power the card on. So you'll notice that we have 1.35 volts at our memory phase. And oddly enough, despite the abnormally low resistance on 1.8 volts, we also have a BIOS splash screen. I'll be upfront and say that I'm a little bit surprised by the fact that we have such a low resistance on 1.8 volts. That's abnormally low, but the card can still post anyways. So at this point, we only have one thing left to do. So let's go ahead and put the cooler on and stress test it. Okay, so as you can see, the card's running, and unfortunately it has one slight problem. So as you may or may not be able to hear, the fans run at max speed, and if we look at our GPU-Z, we can also see that yes, the fans are running at max speed at 3.2k RPM. Believe it or not, this is actually not broken. This is how the card is supposed to perform when it's missing a certain connector. So the connector in question that's missing is one that looks kind of like this. It typically goes over the inside the PCIe bracket over here, but the owner, he either doesn't have it or he never sent it to me. So I'm gonna plug this in and show you that it actually works. So putting in my personal connector. Now if we press the button, notice how it goes off. But if we press it again, it spins at max speed once again. So just to confirm it does run, let's run a game for 20 or so minutes. Okay, so as you can see, the fans work just fine. If we look at GPU-Z, we'll notice that the fans spin at 1200 RPM, and the GPU temperatures are normal. But if I go back and I click this button, it goes back to max fan spin. So like I said, I can't give this button away as this is mine personally. So let's go ahead and try to make something that's similar using, let's say, the reset switch from a motherboard. Okay, so we're looking at the button itself with a microscope. So at this point, we're just trying to figure out exactly what the button does. So I have the button fully pressed down. When the button is fully pressed down, this is when the fans spin at max speed. Anyways, the thing to note is that these buttons, the way they work is that they short pins. So with the button fully pressed down, I can tell you that these two pins are shorted to ground, as you can hear. I meant to say shorted or joined to each other. So this is in order to get the fans to spin at max speed. Now, if we want, say, the fans to spin at a normal speed, we then have to have the button not pressed down. You'll notice that these two pins no longer have continuity, but these two pins have continuity, as well as these two. So in order to mimic this position on the actual connector itself without using the connector, what we're going to do is we're going to use two clear CMOS jumpers. I meant to say clear CMOS jumper caps from some of the dead motherboards I have lying around, and we're going to put them in a position corresponding to these two pins and these two pins. Okay, so as you can see, the card is running a game at the moment. So let's just go over a brief summary of what was wrong with the card. So there were three main things. So firstly, we had a relatively low resistance on 1.8 volts. This typically implies a dead core, but oddly enough, the card seems to work just fine. So the second thing is that we had a relatively, amusing fault at a refin on our UP9509 PWM controller for our memory phase. I say it's amusing because this is being an overclocking card, it's subject to, of course, modifications done by overclockers. And one of the more popular modifications that overclockers typically make is that they will modify refin in order to modify the output voltage of the memory phase so that they can clock the memory higher. So anyways, like I mentioned, it's odd because it seems like maybe somebody changed this in the past, didn't change it back, and it just kept getting passed around as being a dead card until eventually it landed on my bench, where I took the guess that the core was actually alive and decided to try to fix it on camera for everyone to see. And as you saw, the card does actually work. But anyways, the basic idea is that refin is derived from VREF itself. So VREF is 2 volts. These are UP9509s as well as the UP9511 PWM controller used on the GPU V core for a lot of Pascal cards. They have a LDO built inside of them, and they take 5 volts from VCC and then they output 2 volts. And this then passes through a series of components and then ends up at refin, where refin is the reference voltage and the voltage that the VRM itself tries to output. So like I said, if refin was 1.5 volts, the output of its respective VRM would be 1.5 volts. But anyways, as I mentioned earlier, it seems like at some point either the resistor between refin and one of the resistors between refin and VREF died, or more likely somebody modified it and didn't change it back, and the card just kept getting passed around as being broken. Anyways, the fix was relatively simple. We just replaced the resistor with a 200 ohm resistor, which of course meant that we then had a rather normal 1.35-ish volts. I didn't actually check refin, but the fact that the memory phase output was about 1.35 volts means that we probably got it exactly correct. Anyways, the final change that we had to make was that we had to jump a few pins on that custom connector at the back of the card near the display ports. So as you may remember, the fan spun at max speed, which is not what we wanted, and we found that this was equivalent to having the button retracted up top, which caused these two pins to be bridged together, and it of course gave us max fan spin. So the fix, of course, was use the clear CMOS jumper caps from dead motherboards to join these two pins and these two pins to emulate a position in which the button itself was not retracted, but of course not actually connected. And doing this allowed us to have normal fans. Anyways, just as further proof, the fans do work. We can see that there's no connector connected. I used, like I said, the clear CMOS jumper caps from a dead motherboard, and if we look at the actual fan speed itself, it's 1250 RPM, which is more or less what it should be given the temperatures and the load. I should note that the card still has one more issue. The LCD screen up top doesn't work due to a dead microcontroller, but since the microcontroller has firmware in it, which I can't get, at least at the moment, I wasn't able to fix it. Anyways, I hope you learned something watching the video. I apologize for the length. It was much longer than I thought it would be. And in either case, I do hope you learned something useful. If my channel or my videos have helped you out, consider becoming either a patron or buying something through the Amazon affiliate link. But otherwise, hopefully I will see you in the next one.